this video, we're going to explore two other carbon-based nucleophiles. The first one is based on the carbon-carbon triple bond, and the other is based on the cyanide nucleophile. So first of all, let's turn our attention to the carbon-carbon triple bond. As you may remember, alkynes can be considered to be relatively acidic. The pKa for a typical alkyne is on the order of 25. Now, to remove completely this proton, we still need a pretty strong base. The amide anion is a good candidate. The result of removing the acidic proton from the acetylene or the alkyne would generate, in addition to the acetylide anion, the ammonia conjugate acid. Now, to get a sense of to what degree this reaction moves forward, the pKa for ammonia is on the order of 35. So we can do a quick calculation of K equilibrium. You may recall from first semester it goes something like this. pK equilibrium is equal to the pKa of the reactants minus the pKa of the products. The pKa of the reactants is 25. The pKa of the products is 35. So 25 minus 35 is equal to minus 10. The way that we translate this into a K equilibrium is that K equilibrium is equal to 10 to the negative pK equilibrium. So therefore that's 10 to the negative 10, and therefore we would expect the equilibrium constant to be on the order of 10 to the 10. This of course means that the reaction essentially goes 100% to the right. Now, I show you the origin of the acetylide anion, but I'm quite happy if you start your reaction mechanism, or actually even saying what reagents you need, by just directly drawing the C triple bond C negative. You could also, for instance, show that it has a counter ion as such, but you don't need to start from the original conjugate acid and show the amide base pulling off the proton. Well, now that we have this negatively charged carbon, we have, of course, a very strong nucleophile. And just like what we've seen in the other cases, this strong nucleophile can attack at our carbonyl, the pi bond as an electrophile. For completeness, I'm going to write in a lone pair of electrons here, and now I'm going to show this attack at the carbonyl. We form the intermediate with the negatively charged oxygen. And of course, the next step is the aqueous workup. You may have noticed that I'm using a different acid here rather than simply writing H+. The idea is that we should, in principle, use a relatively weak acid. And certainly the ammonium ion falls into that category. So this would represent the aqueous workup. Now, you may be wondering why it's important to use a weak acid. You may recall from first semester that a triple bond in the presence of aqueous acid can actually result in the addition of an OH on the more substituted carbon to form the enol. That enol will then undergo tautomerization to form a ketone. In other words, the triple bond can react further in the presence of an acid. If we use a weak acid, the conditions are such that the solution is not too acidic, thereby reducing the chances that the triple bond will react in a substantial way. So here you can see ultimately our product. Now at first this may look a little strange, but perhaps you'll get used to the idea that if you end up with an alcohol on a particular carbon, and then on the adjacent carbon you have a triple bond carbon-carbon, then you know that it's the result of an acetylide reacting either with a ketone or with an aldehyde. As a summary of this reaction, let's look at the next slide. So here you see we're starting with the aldehyde, and to form that particular product, one of the ways that we can represent this is to show indeed the 3-carbon nucleophile involving the triple bond. If you want, you can also include the counter ion, although not entirely necessary. And of course, that would be step 1. Step 2 would be the aqueous workup with the reaction involving our weak acid. Now, if you can't remember this ammonium ion as a weak acid, one of the things that you could do is just write weak H+ or something like that, just to let me know that we're concerned about the reactivity of this triple bond. Now, one of the interesting things to do is to look at a particular product and try to take it apart to see what reagents would have been used to synthesize that product. So as in case in point, let's look at the next exercise. So here we're trying to imagine how we would synthesize these compounds, either from an aldehyde or a ketone, and the corresponding alkyne. So first of all, it would be a good idea to actually have the structure. So you can see we start off with a 5-carbon chain, and on carbon number 1 we have the triple bond. On carbon number 3 we have an alcohol, and then of course we have carbon 4 and carbon 5. So that's our final product. So in a sense, what we're doing here is something like a retrosynthetic analysis. What I would do is I would look at the carbons that are involved in making a bond to where the alcohol group is. Because where the alcohol group is where the carbonyl would have been. And in a sense, we want to sever that bond. So the idea is that we want to sever this bond, pull it apart. So if I now pull it apart, I'll see that on one side, I have a 3-carbon aldehyde. On the other side, I'll have a 2-carbon alkyne. And of course, it would have been a negatively charged alkyne, or the acetylide anion. So combining these two components in a nucleophilic addition reaction would form the desired product. You may want to stop the video and see if you can discern what the original reactants would be to form this second product. Okay, so let's write the structure for the second product. In this case, we actually have as a substituent a benzene ring, which we have said is 2-phenyl group. So on carbon number 2, we have both an alcohol group as well as a benzene ring. Let me just put this together. So there's my benzene ring. Of course, you can just represent that as a pH to indicate the phenyl. On carbon number 2, I also have an alcohol group. On carbon number 3, I have my triple bond. 1, 2, 3. And collectively, you can see that I've got 1, 2, 3, 4 carbon chain. So that corresponds to the bute. So this is what we want to make. And once again, I'm going to sever the bond between the carbon that's making the alcohol and the carbon involved in the triple bond. So I'm going to sever this bond right here. I can see that what I'm left with, and I'm going to draw out the full benzene ring once again. So here's my benzene ring. It's attached to a carbon that is now an alcohol in the product, but originally would have been a carbonyl. And that in turn is also attached to another carbon. So in this case, in order to form that particular alcohol in example B, we need to start from a ketone. And once again, the nucleophile that would have attacked that ketone would have been the 2-carbon acetylide anion. So one of the things that you might notice is if, right here, this product, if we have a secondary alcohol, well then, of course, it came from reacting initially an aldehyde. By contrast, if we have a tertiary alcohol, then there must have been a reaction that involved a ketone. Of course, again, this is not something to be memorized. You can work it out. But the more examples you see of this, the easier it will be for you to easily make that connection.